Okay, so we are going to import a stat models dot formula dot API as let's create a simple, more simple actually name for that. Okay, we are going to import this. This is a statistics package. Okay, so what I'm going to do, I'm going to create a model. So model formula can help me to create my model. So OLS, this is an ordinary regression model. Let's write down here OLS, ordinary regression model. Okay, from stat model formula API. Okay, so what I'm going to do, I'm going to get calorie, and then I'm going to use tilde, and I'm going to use sugar. Then, did you see what I'm missing? I'm missing data here. Data is equal to our data set. Now everything works. Now I'm going to feed the model. While you are creating the model, you can feed the model too. Now let's explain this one. It says y tilde x. So if I had more than one one explanatory variable, I would have x1 plus x2, for example. If I had more explanatory variable, I would use this model. This is just example because our model can be different. We can compute interaction between them using multiply, or we can do kind of transformation, all of this. Okay, so this is just example. So if I have one explanatory variable, it goes on the right side of tilde, and the response variable goes on the left side of tilde. Okay, so I have model. I'm going to print in the summary of this model using summary. So what I see here is the R square, which we saw in previous lecture. Where is that here? R square, right? And then the adjusted R square, we will talk about that later. The F statistic, p-value, log likelihood, AIC, BIC, all of this. These all help us to choose the best model. Let's say I create 2-3 different models, and let's say my second model will be the transformation of sugar on Y based on whatever problem I see in my current model. And then I want to compare the next model that I'm creating with this current model and see how my model improved. Then I will look at all this information here: AIC, BIC, log likelihood, all of these kind of things, p-value. And here we have the intercept, which is 89.82. Let's look at this. Here also we had 89.82, and then a slope is 2.4, and then if we go back, you will see a slope is 2.4, right? Well, everything is fine. Yeah. So for each of these, for intercept, I will see the p-value. For sugar, I will see the p-value. So what p-value says, if p-value is less than a certain level of significance, we will talk about that also. I will, if p-value is less than a certain level of significance, I will say the sugar has a meaning or significant effect on calories. So if I had more variable, those also would have a p-value, and then I would explain the p-values and based on the other variables, other explanatory variable. And this one also shows some of other information about the model. Okay, so this statistic package is very good, because later when we want to improve our model, we can use this. And then the other thing this package shows, actually that's another package, import stat. It's a stat model package, but I'm not using formula anymore as a stat model. And then I'm going to create a figure. So what I'm doing here, I'm going to create the graph of residual. As I said, after we fit the model, we must have a graph of residual to see how our model is explained by the explanatory variable. I'm going to say stat model dot graphics. So I'm using the attribute graphics, and the plot regress EXOG. These are all the attributes of a stat model. And then I'm going to mention the model I'm using, and then my explanatory variable is sugars, because I want to see the residual of sugar, and using the figure. Okay, good. So this is the residual plots. So these are something we need to have to explain our model and how our variables are the correct variable in the model. So the top right is the residual versus fitted plot. So y is the residual y-axis, and then what is the x-axis is fitted value. Okay, if the residual appear to be randomly scattered around this zero line, this is a zero line, without any visible pattern, this would be an indication of a good, it would be a good sign. It would be indication that we don't have the problem of heterodacity. If we see like something like funnel shape, like as you see here, we have a kind of shorter boundary, and then it appears to be kind of increasing as the sugar or fitted value are increasing. So it's a kind of funnel or cone shape. So if we have that kind of problem, that is the problem of heteroscedasticity, and it's not a good sign. Means there is a variability that we have to be dealing with. Well, we actually talk about that in detail also. Heteroscedasticity means the unequal scatter. So when we face this problem in the context of the residual or error term, means we are seeing a certain increasing or decreasing pattern in the residual, the way you see here, kind of. So because regression analysis assume that all these residual are drawn from a population that has a constant variance, they call that homoscedasticity. Means constant variance, which is the opposite of heteroscedasticity. So therefore, to follow this assumption, constant variance, to follow this assumption, the residual should have a constant variance, and plots should not display any pattern, any particular pattern. So what we are willing to see, we are willing to see the residual versus fitted value, which is this one, are uncorrelated and kind of uniform. Otherwise, model has a problem and the results are misleading. The model is misleading. So now, the kind of vertical range of the residual here will kind of increase. If you see here, this is higher. Actually, we have a outlier here, right? But if we ignore this outlier, you will see the pattern is kind of smaller vertical kind of distance in compared to bigger, kind of larger vertical distance here. And what heteroscedasticity tends to cause, it will kind of cause a p-value to be much smaller than it should be. Like the way we see here, the p-value is almost 0. So there is some problem here. And also, why it does that? Because we never talked about t-value, f-value, which are the statistic kind of, we never talked about that, but they cause this statistic kind of to underestimate the amount of variance. So when these kind of statistic underestimate the amount of variance, they will have a kind of bigger value, t-value, f-value will be much bigger, and then those f-value and t-value causes the p-value to be smaller. These are kind of very kind of detail of a statistic. If you take the statistical analysis, data analysis 1 or 2, you will understand these concepts more. But we will go through p-value, and very briefly we will talk about that later after we talk about the basics of regression model. So this problem can lead you to kind of conclude that a model term is statistically significant based on this p-value you see, but in reality, no, it's not. It's just the error of kind of variability that caused the kind of false result for us. And there are kind of multiple solutions to kind of decrease the problem of heteroscedasticity. One of them is, for example, redefining the variables, and another is weighting variables, another is like transforming the dependent variables. So these are some kind of way you can kind of fix the issue of variability in residual, which cause a kind of misleading information of p-value, and it kind of misleadingly says for example, sugar has a significant effect on the calories. Okay, so if we have more time during the semester, we can talk about the variability and heteroscedasticity more. But if you are interested, and when you are dealing or working on a project that depend on this kind of interpretation, you can study this topic further, because there are many information online on internet that is very useful and can help you to understand this. Okay, so now we want to try protein versus calorie. So let's say we are importing stats models API as stat model, and then we are creating a new model using model formula. Actually, where is model formula? This one. And what we are doing now, OLS, and then calorie. This time the X variable is protein, and our data is the data set, and we are going to fit the model. This model is based on protein as a explanatory variable that can have effect on the response, right? And then what I'm going to do, I'm going to print the model dot summary. Let's have a look at summary so quick. Oh wow, so r squared is 0, means the variability on calorie that is explained by protein on the that's explained by the model, which is this model, on the protein is a very kind of it's not, model is not explaining the variability of calorie. And then what else? We will see the p-value is 0.86 for protein, and this is the intercept coefficient, this is the protein coefficient. So let's continue, draw a plot also. Dot figure, and figure size is equal to 12 and 8, and then I'm going to use this figure and stat model to use the graphics and the plot regression and EXOG, and then model, and then the variable, explanatory variable is protein, and then I'm going to use the figure created. Okay, so let's see what happens. Okay, so well, there is kind of pattern, but let's first talk about the p-value and then we can go back to this. Okay, so about the p-value, where's the p-value? Here, this is the p-value. Okay, so well, there are some concepts we definitely should understand first to be able to explain the result that we see in this chart. So one is let me write down level of significance. So what is the level of significance? We actually show that with alpha. This is the probability. This is a probability of what rejecting the null hypothesis when null is true. This is the smallest p-value possible. So level of significance is the cutoff also for making decision on, let's say, rejecting or not rejecting the null hypothesis. And this actually will be compared with the p-value. So if p-value, for example, is less than alpha, we reject the null hypothesis. If p-value is greater than alpha, we cannot reject the null hypothesis. And alpha is typically equal to 0.05. It can be 0.01, 0.1. It can be any of this value. Or when we say 0.05, we mean 5%. At 5% level of significance. So now, what is null hypothesis? So null hypothesis says the explanatory variable and the response variable are not correlated, or we can say they are not associated. In another word, we can say there is no effect of explanatory variable on response. There's no effect, or there is no relation. So I explain it as claim of equality. Okay, so if I reject the null hypothesis, it means the explanatory and response are associated, correct? Or we can say there is a effect of explanatory on the response. Means the explanatory can change the response variable. Explanatory can cause a change in response variable. So this is a null hypothesis. And there is a claim, we call that alternative hypothesis, which is a claim comes from population. So scientists, people will claim something which is kind of, if we reject the null hypothesis, means we cannot reject the claim come from population. If we, for example, cannot reject the null hypothesis, what we are doing, we are rejecting the claim made from population. Okay, so now what is the p-value? P-value is a probability. This is a probability, actually probability that indicates if we have a strong or weak evidence against the null hypothesis. Another definition says is the probability of obtaining results at least as extreme as the observed results of the statistical hypothesis test. So this is a statistical hypothesis test, like test statistic or test statistic. So these are something we're going to go through them later. And then all of these assume that the null is correct. Okay, so in our case, when we have the p-value which is 0.869 in the example of relation between protein and calorie, when p-value is 0.87 approximately 87, 0.87 is greater than 0.01, right? So if p-value is greater than alpha, we have a large p-value. So when we have a large p-value, then we cannot reject the null hypothesis. So what was the null hypothesis? Null hypothesis says here, it says explanatory variable and the response are not correlated. So we cannot reject this, right? In parentheses, this is the null hypothesis. So therefore they are not correlated. The explanatory variable and response are not correlated. Therefore, the explanatory variable, which is protein, and the response variable, which is calorie, are not correlated. So they are not associated, they are not correlated. So the other case, if p-value was small, we could reject the null. So we could reject the null and say the x variable and y variable are correlated. So let's say the example was, let's say we didn't have a problem of variability in the previous example, in the example of sugar and protein. So what was the p-value? P-value was very small, 0, right? Let's say we didn't have any problem of variability. We could say sugar and calorie are associated, right? And then remember, p-value is small means p-value less than or equal alpha. P-value large means p-value greater than alpha. So what happens here? Reject the null, cannot reject the null. So when I say reject the null, I means we have enough evidence to reject the null. But here we don't have enough evidence to reject the null, right? Okay, so this is explanation of p-value, null hypothesis, all of this. So I hope you understood this, and we will go through all of this again and again. If you have any question, let me know. And then next time I'm going to start talking about multiple regression, and maybe we will more talk about the curvature form and linear form of the regression, least square regression line. Okay, take care of yourself. Have a good day.